Well, thank you again for the Australian Space Frontier Society. Is that it? I hope for allowing me to talk here. Thank you so much. I'm Joe Khachan from the University of Sydney. I'm an experimental plasma physicist, and plasma physics covers anything with plasma, including that is laboratory plasma. Eva is the space plasma physicist. So one of the things it covers is electric propulsion, which I shall talk to you about today. What you see there in this first slide is something called a Hall effect thruster, which is the most popular electric propulsion system for spacecraft. I'll talk a little bit about that, but then I'll talk about what we have been doing in terms of electric propulsion. So that didn't move. Okay. So the reason it's called New Frontiers, electric propulsion is old. In fact, propulsion is old. If you've ever used a garden hose, you pretty much know what propulsion is about. Water goes one way, you go the other, if you've got a fireman's hose, that is. So the reason it's a new frontier is because since 2003, there's been a new generation of satellites. They're called nano-satellites. And this is what's called a CubeSat because it looks like a cube. And it looks like something you would go to Hobbyco and pick up. It looks like a toy. And initially you could not take them seriously because you have images of satellites that weigh many tons, can stream live television networks and all that sort of stuff. What can a toy like this do? And I'm about to show you today. And I'm about to show you where propulsion fits into powering this toy. So that's a CubeSat. It's 10 centimeters cube on the edge. But naturally, you find when you want to put it into space, it's not worth your while having one cube. So this is three cubes together, and next to it is my standard oversized coffee mug that I use as a measure for everything. And what you'll see is that the size is about right. There are three cubes there. You see the solar panels on the outside. This satellite, what you don't see is a method of propelling it, moving it around. I'm about to tell you that generally you don't need to. So why are they called nano-satellites? It's just a label they put on satellites that are between 1 and 10 kilograms. The CubeSat I showed you initially is a picosatellite. It's less than a kilogram. The nanosatellite, the 3-unit one that I just showed you, is actually between 1 and 10 kilograms, and it's a nanosatellite. And that is mostly what we've been doing at the University of Sydney and other places around Australia. A microsatellite is has a larger mass, as you can see, 10 to 100 kilograms. And then you get into small and medium satellites. If I could mention the Starlink satellites that you would all have heard of for one reason or another, they are actually small to medium because they're about 250, 260 kilograms. Sputnik was a microsatellite, the first satellite that was 83 kilograms. So, but now you think, oh, well, they've already been doing microsatellites. Yeah, mostly not. I'll show you in a moment. So we're dealing with nanosatellites, and how do you get to position them in space? So what I said previously, it's a toy. It's not really a toy when you start looking at the market value of these spacecraft. No. So if we're looking at nanosatellites, that's the purple one, and the microsatellites, that's the light blue one, you'll notice the nanosatellites have a larger market share. Now, notice it says the word mass. That is just the amount of stuff, the amount of satellites you're producing. It says nothing about their revenue. The revenue is much higher than, so the mass value is $3.9 billion in 2024. And as you can see, it's rising by about 22.8%. And so it's a growing market. This is not a toy. You can do a lot with it, and I'll show you what you can do with it. But incredibly, those tiny satellites are dominating over the microsatellites. And at the moment, they're worth $3.9 billion for the mass. but much more, about 2 or 3 times more for the revenue. So it's big business. It's not, and it's growing. So they are worth taking seriously and not considering them a toy. So how is Australia doing? So the biggest revenue share is North America. It's 43.7%. The light blue is the fast growing markets, and you'll see Australia fits into the darker of the light blue. So we are sort of gaining ground in terms of these nano and micro satellites. Now, what can they do? And why do you need to take them seriously? You should take them very, very seriously, because I've picked on one particular company called Planet Labs. Now, I didn't choose that at random. That company was founded by one of our former physics students, PhD students from School of Physics at Sydney University. So being biased, I chose the company that he co-founded, which is Planet Lab. And they, as of last year, their revenue per year is something like 260 million, something like that. That's not small numbers for a tiny company. And their business is nano-satellites. And these are some of the things they do. They can do Earth observation. So they can do wide field observation. They can narrow in to even show you the ships and the containers and whatever's happening on a port. So they can do large field imaging, zoomed in imaging. It's not just imaging. If you look at this graph on the right, it can determine soil moisture. Now, what you see is a graph of soil moisture over time, but you can superimpose soil moisture over an image of the land. You can also superimpose an image of methane emission over the land, or many other chemicals emanating from the land. You can look at deforestation. You can look at what type of vegetation, not just by imaging, by superimposing optical spectroscopy onto the imaging. That's fantastic information, and you can imagine all sorts of arenas where that's useful. Even if it's just disaster monitoring fires, bushfires, it's incredibly helpful. What they have over the very large satellite, the satellites that are like 6-7 tons or something like that, first of all, they are at around 500 kilometers altitude. Those huge satellites, they're at 35,000 kilometers. So signals between ground and satellite, these nano-satellites travel much, much faster between them and ground. They've also, because they're so cheap, that a university department can afford to do them, they send up hundreds of these, and they're constantly circling the Earth, giving you almost real-time images and video of all this information and more. So you can start to see defense might be interested, agriculture might be interested, all sorts of departments might be interested. And you can obviously also do mapping of sorts. So all of a sudden, it's big business. They do a lot of useful stuff. They're not a toy. Okay. I wish I could tell you, I wish I could spend more time about the exciting things that they can do. A lot of exciting things are happening. But I'm here to tell you about mundane things like how do you control them, which is what I'm about to tell you. So standard on all of these nano-satellites, and even on larger satellites, but these are miniaturized for nano-satellites, are things that can control the attitude, basically how it rolls, how the satellite rolls. You've got things called magnetorquers. What you see here is 2 solenoids. These things create a magnetic field that interact with the Earth's magnetic field. There's actually a third coil neatly hidden underneath there. There's an X, Y, and Z coil to enable you to power these electromagnets that will produce a force that, with the Earth's magnetic field, and then rotate them along whatever axis you want. But that's not enough. Sometimes you have to slow, when you rotate them with the solenoid, you have to sort of, what they call dump momentum, stop them from rolling. So you've got these other things called reaction wheels, X, Y, and Z. You rotate one way, the satellite rotates the other way. So with a combination of reaction wheels and magnetorquers, called the attitude determination and control system, You can control the orientation of the satellite, and it's extremely important. I don't know if you've seen footage. You can still say that word, footage. I don't know if you've still seen video of the satellites being launched in space. They're tumbling like you don't believe. They're absolutely tumbling because they have no control. They shoot them out, and these things are just tumbling. And it's these devices here, the magnetorquer and the reaction wheels, this attitude determination and control system, detumbles them. And then you can start to give commands to the satellite from Earth as to where you want them to look. If there's a camera that needs to look on the Earth, you can. If there are telescopes that you need to orient towards the stars, you can. So now you can start to orient the satellite in whatever application you want. However, that's not enough if you want to do extra things. It's mostly fine. You don't need anything else for most satellites. The trouble is, sometimes you need to change the orbit of the satellite. Sometimes you need to coordinate the motion of multiple satellites. That is, say if you're an astronomer and you need to do something called interferometry. You need 2 or more satellites with a precisely determined position between them, staring at the stars. You need to control those positions. You cannot do it with the attitude control device. You need propulsion systems to translate the satellite, not rotate it. And this is essentially what I'm going to tell you about today. What do people do, and what are we doing? What you see here is a cartoon, as you can see, but it's not fiction. These things that are coming out of here, I will talk in a moment, and I will show you a commercial device that does it. They're called field emission propulsion systems, and they're good. So you might think, what's the big deal about propulsion? We can get rockets into space. So we can get rockets into space. We have these rocket engines, problem solved. Okay, so let me give you an indication of why a problem isn't solved. I can't find a better image. I can't find a better looking image than a space shuttle. All other rockets look boring, so I've kept the space shuttle, although it's no longer operational. The space shuttle has maybe 1,000 tons of fuel on there. They're burnt in about 8.5 minutes to get you into orbit. The fact is, chemical fuel burns, it provides a lot of force, but it burns very, very quickly, and then you're done, you're finished. But the additional thing is, the exhaust speed of that rocket fuel is maybe 1 to 4 kilometers a second, which is fine. It'll get you off the surface of the Earth. But if you wanted to do interplanetary travel, including with little microsatellites, you can't go directly to a planet like Mars with this sort of exhaust speed. I won't bore you with the celestial mechanics of it, but it turns out you need, for each destination, you need a minimum of exhaust speed. For Mars, you need about 10 kilometers a second, roughly. But you're saying, but they go to Mars. They've sent the Voyagers. They've sent everything. Yes. What they do is they use tricks. They pick up speed by using the gravitational field of planets. So they go on they go on round trips to pick up that speed. It would be so much better if you can go just directly to your destination. That you can do, provided you have a method of getting that 10 kilometers a second. Sorry, I seem to have lost the map. There it is. And so what is the problem with chemical rockets? They're great. Chemical rockets are fantastic. They've got a lot of thrust on them, a lot of force. The trouble is, the energy you can supply per atom is fixed. It's fixed by the energy in the chemical bond. That's it. But there is a method where this restriction is lifted, and this is the method of electric propulsion. You are not limited by the energy in chemical bonds. You're limited by the amount of power you can put in. And then you can supply as much energy as you like for a particular atom or ion. So a propulsion system that does it, very popular. This thing has sent spacecraft to other planets. In fact, one of them sent a spacecraft to the moon, the Smart 1 spacecraft. spacecraft, which started in low Earth orbit with this Hall effect thruster that you see here, operating on xenon gas, and they went to the moon. They started in low Earth orbit, go to the moon, which was the point, to show that you can. And so how do these things work? Well, I'm about to tell you how it works and why this can't. This is very, very popular. It's very efficient. Trouble is, it can't work on a nano-satellite, and that's your problem. So first, before I can tell you that, I need to tell you how electric propulsion works. It's actually very, very simple. You take a gas and you strip all the electrons off the gas. That is, you ionize them. And then you put those ions between two electrodes, a positive and a negative electrode. This is a grid, if you like. It's got a lot of holes in it. And they accelerate the ions, and whammo. The speed, you just dial up the speed. The voltage you put on the grid is the speed, determines the speed they will get. Easy. I can dial up whatever speed I want. I'm not limited by the chemical bonds. And you might say, well, why don't they do that on Earth? Trouble is, these work at really low pressures. If you put them in 1 atmosphere, they just don't work. So you need them to work in space. The trouble is, if you think about it, there's positive charge leaving, but negative charge is left behind. Over time, that negative charge builds up in a spacecraft so high that will start dragging back the positive charge and your propulsion will stop. So for this reason, they have a thing called a neutralizer that emits negative charge, electrons that is, and they go out with the positive charge. And so that way you can keep producing ions and propelling them forwards. So this is a cartoon of that Hall effect thruster. I'll point out there's the neutralizing device called the cathode. And they're really clever about, this is a Russian invention, which now the whole world has adopted. They don't have a physical grid. The electrons do two jobs. The electrons are caught by magnetic and electric fields, and they circle around, and they act as a grid to accelerate the ions outwards along this electric field. And they also go with the ions to keep them neutral. So they do two jobs. A very clever invention, doesn't require physical grids. Trouble is, if you try and operate it below 50 watts, it just doesn't work. People have tried. In fact, at 50 watts, it's terrible. They usually operate at 1 kilowatt, and they're fine for large satellites and large spacecraft. They're great. I don't think you need to search anymore. That's the thruster. So here it is. That's the neutralizer that I just pointed out, and that's the plume of positive and negative ions providing propulsion to the spacecraft. Where do we come in? The gap in the market is this. There are very few propulsion systems for these nano-satellites. You need to operate at around 1 watt or 2 watts. 50, not even 50 watts. Generally, you don't have 50 watts available to you. If you've got a 3-unit nano-satellite, that will maybe have 10, 20 watts available to you. And you might say, well, good, use that. Well, you can't hog the whole power. There's so many payloads on there. Everybody's testing their payload. They'll allow you 2 watts, as they have for us. And that's fine. So now you're searching for a technology that can work at around units of watts, provide decent propulsion, and all of a sudden you have a very few on the market. But they are gaining ground. People are trying to make a business out of this. So here's where we come in to something called the charge exchange thruster. It starts out like anything else, like any other electric propulsion system. You take a gas and you strip off the electrons, the blue dots there, and you strip off, and then you're left with the ions, the positive red circles there. And there is an electric field. There are electrodes, positive, and this conical thing is negative. And you accelerate the ions towards that negative thing, and it has a hole in there for the ions to exit. So far, no difference to any other electric propulsion system. But as I showed you, you need to neutralize it. You might say, where's your neutralizer? That's the invention. The neutralization is really subtle. The neutralization occurs because this conical structure, it has 2 jobs. One of its jobs is to keep the gas pressure higher than the pressure in outer space. So, because the gas pressure is high, there are quite a few neutral gas particles symbolized by the green. So the positive ion, the red particle, travels through the gas, and they come, and this is a quantum mechanical effect. If that red particle, the ion, comes very close to a neutral gas particle, the green, under certain circumstances, the electron from the neutral particle finds it really easy to jump across to the ion. This is a process called charge exchange. When you work out the equations for this, they are quantum mechanical equations. It's not a classical effect. People think, oh, isn't it like a billiard ball? You know, this striking that? No, you would lose energy that way. It's very much like a drive-by. The ion is driving by, and the electron from the neutral particle jumps across to the ion. And what you end up with, the green particle here was the red particle there. So the ion becomes a neutral with the same direction and the same speed, but now can exit the spacecraft without having to worry about the charge. That's the invention. We call it the charge exchange thruster. And of course, ions are left behind, which themselves can accelerate, charge exchange, and go out as neutrals. So that's a charge exchange thruster, which I'll tell you a little bit about. And that's the innovation that we've had at the University of Sydney. And I'll tell you how that came about. So, so just a bit more detail on the cone. It's funny. It's a very simple technology, just a metal cone that causes the electric potential to drop, which means ions fall down that potential, that is, they get accelerated. And moreover, that cone can enclose enough neutral gas, in this case hydrogen. There's a hydrogen ion coming very close to a hydrogen molecule. It picks up an electron, so it becomes a neutral hydrogen atom. That's what the asterisk is there. And what remains behind is a low energy hydrogen ion. So this is charge exchange, and the question, and this is the history of it. This is 2007, working with of course, as these things start off with an undergrad student, third-year student. We came up with this really clunky thing. This is probably the size, or just about the size of a 3-unit CubeSat. But here it is. You've got electrodes, anodes, and cathode. They're the cathode. That's the conical electrode. This has glass as an enclosure. There's a gas in there. You get ionized. It gets accelerated and ejected as a beam of neutral atoms and molecules. So at the time, we thought, oh, isn't that neat? I wonder if it really is ejecting at high speed. There's a way to find out. So if you're into astronomy, you're probably familiar with the hydrogen H alpha line. If you're not into astronomy, don't worry about it. Hydrogen, or if you looked at the sun with a red filter, the H alpha filter, you will see this line, this spectroscopic line. What it is, it's a red line that's being emitted by hydrogen atoms. It's at 656.3 nanometers in wavelength. And then you see something odd to the side. Well, I've got to tell you, that big lump of spectrum to the side is also actually the hydrogen H alpha line. It just doesn't look like that nice narrow line, is because when hydrogen atoms are screaming at you, are like just heading towards you, the wavelength gets shortened by a process called the Doppler effect. The wavelength gets shorter, and you might say, okay, well, it got shorter, but why isn't it a narrow line to the left? It's because there's a distribution of velocities. Those ions being accelerated could be starting from anywhere on that potential hill. So there's a distribution of velocities. So from that, this is basically several spectra of a different power applied to the device, but the features are the same. So what you see is a distribution of velocities that you can get from the wavelength. What's the average velocity? 300 kilometers a second. This is a far cry from the 4 kilometers a second you can get from a chemical rocket. In fact, we dial that up full blast, 300 kilometers a second. We can turn it down to 100 kilometers a second. We can turn it down to 50 kilometers a second. We can dial up whatever exhaust speed we want. So it was that spectrum was taken from that image that I showed you of the first charge exchange thruster. It was ejecting neutrals at extremely high speeds. So the thing is, it works. You can make a thruster that's self-neutralizing, that ejects atoms and molecules at really high speed. Now, here's the question. Can you shrink it down so you can put it on a tiny part of a cube in a nanosatellite? Well, I wouldn't be here if the answer was no. So the answer is yes. Here it is. What I do have, and then I'll hold out. So for the people online, I'm just holding it in my hand. So here it is. This is the charge exchange thruster. It's 10 centimeters by 10 centimeters by about 3.5 centimeters wide. And you feel free to look at it later. This is actually a working model. It's got fuel in it. It's operational. It can be flown on a satellite. Until we start with electricity, in which case the electronics will be fried and we can't. But anyway, so what happens is, this is what you might be saying, where's the conical nozzle? It's all inside the box. The hole here, the little aperture, inside it there's a conical nozzle that you don't see. So let me give you another view of this. So again, here's my standard mug, oversized mug that I use to measure with, on a seat that I sit on, a bit worn. This is the other side of it. Here's again the aperture where the plume comes out. What you see here are the electronics. What do these electronics do? They do all sorts of things. They control the power supply. They control the fuel supply rate. These are valves that can turn on and off the fuel that can go to the thruster. The electronics also can communicate with the payload computer that's on the satellite. So it's a fully functioning system. You can sell this thing. It's a product. So how did this come about? How do you go from being a clunky university academic with your undergrad students fiddling about with junk? How do you go from that to making something like this? You need money. You need money to do it. So how do you do it? So I will show you in a moment. So here it is. Thank you, Tony Munger, for taking these images with his excellent camera skills. This is, as you can see, here's the electronics of the charge exchange thruster. You can see the plume, but it doesn't, it's sort of foreshortened here. So let me show you to the side of it. So here's the plume to the side. And indeed, when we do Doppler spectroscopy on these, and this is hydrogen that's coming out. That hydrogen is absolutely, the exhaust speed is like 100 kilometers a second. It's absolutely screaming. So how do you make it happen? All right. So you start to look, how do you compare commercially? What's on the market? Well, it turns out large companies and startup companies have been active, because when they see the increasing market and the increasing revenue you can get from these nano-satellites and the applications you can have when you have a propulsion system, this is one that I think is particularly good. This is called a field emission electric propulsion system. That's an old technology. They put it on large communication satellites. You know, when you get satellite television and that satellite is 35,000 kilometers away, they use these things for attitude control, for what they call a station keeping. So these things have to melt metal. They have to have liquid metal. They eject outwards metal ions, but they also have to neutralize that. So you have to spend energy neutralizing those metal ions as well as accelerating those metal ions. Fine, but they work. Now, this was made for a CubeSat. It's made by, you can see its dimensions. We're at 10 centimeters by 10 centimeters by 8.25 centimeters. So it can fit in one of the cubes of a nanosatellite, of a CubeSat. And here's our thruster. Now, I've picked out some values that we can compare. We have measured in our laboratory, and I won't bore you with all the technical details of how that was done, but an apparatus was made to measure it. At the 2 watts we're allowed to have on this thruster, we can produce 5 micronewtons of thrust, which doesn't sound like a lot. But keep in mind, this is a commercial thruster. It has a range of thrust, 10 micronewtons to 350 micronewtons, but the thrust that you get is a function of the power you put in. So let's look at what power they can put in. The minimum power is 8 watts. Well, that won't do, I'm afraid, for our particular nanosatellite. because we just wanted units of a couple of units of watts. Nevertheless, let's compare. The lowest power, 8 watts, can produce 10 micronewtons. That's actually not bad. Now, Hall effect thrusters, the one I showed you previously, they can produce per watt 50 micronewtons, but that's when they're operating at a kilowatt and more. When they come down in power, it's the law of plasma physics. Your thrust is going to come down. More power, more efficient thrust. That's why they don't work for nano-satellites. However, this one, this field emission propulsion system, look at that. 10 micronewtons per 8 watts, 10 on 8. 500 micronewtons on 2 watts. We're not doing too badly with our thruster. It's competitive. Can we have greater thrust? Yes, of course. If you allow us the power, we will give you the thrust. Whatever, that's basically the bottom line. But in this case, you're probably saying, what's stopping you? Okay. So, maybe you have heard, I'm sure you have heard, at the main node of the Centre for Uncrewed Air Vehicles and their Applications is at the University of Sydney, but there are many other nodes. This centre, it's, as the name suggests, it has these UAVs, but also one of the major aims of it was to produce satellites that can go into orbit and deliver some payloads. So we have a satellite. And there's a website. If you just go to Google, type Quava, it'll come up. First hit will come up, and you can see all sorts of payloads that are on there. So the charge exchange thruster, I said, how does it come to be? It was funded by this centre. This centre funded materials and, most importantly, funded a skilled experimental plasma physicist to be able to produce the thing I showed you. Without the Quava funding, it would still have remained as a clunky little student experiment. So, with Quava, Quava has now launched 2 satellites, Quava 1 and Quava 2. Currently in orbit is Quava 2, launched in October of last year, and the charge exchange thruster was on that. Now I need to show you Quava 2. When it was being loaded into its deployer, the thing that will deploy it to space. So what you see there are the solar panels, to power the thing in space. And you see several things poking out. Some are spectrometers, some are cameras. There are different payloads on them. There's a radiation counter in there to measure radiation in space, and that's producing interesting results. But what you'll see here, this tiny window, you see that characteristic aperture of the charge exchange thruster. Notice its position. Its position is slightly off center. So what do you do when you've got a thruster? Yes, indeed. So what it'll do, it'll rotate the satellite. And you say, oh, that's boring. Why don't you make it like change? Why don't you just make it change orbit? Happy to do that. All the other payload owners are going to get angry at you. So you don't do that. All it is we need to test that it works in space. And the reason you do that is because they have a thing called technological readiness level. If you can show it works in space, then you've reached the highest readiness level, which means it can become a commercial product. So that was the aim of the Quava satellite. And so, yes, it's off center for a very good reason. It was supposed to spin the satellite and therefore show that it actually works in space, not just in the laboratory. You might be saying, well, you said it was launched in October, and have you done it? Trouble is, these satellites are also subject to the radiation in space. So radiation damaged the payload computer, and the payload computer is the computer that talks to a lot of payloads. The only payload it doesn't talk to is the radiation counter, which is still operating just fine. But unfortunately, the charge exchange thruster could not be operated. We could turn it on at one point and it powered up, so it was working in space. But unfortunately, the payload computer just failed, and we're not able to operate it in space. So I wish I can give you great news, but I cannot. So with that somber note, I will take questions, and Now, I'm not sure if I can hear the people online, or maybe Wayne.
Some stuff come up in the chat, so can you pull the chat up that's in the box there?
Can I? So I think I'll come over to your screen and have a look at the chat.
So you can chat.
Okay.
So if you click on the box over there on the.
So why has this gone? Oh, this has gone dark because of. So.
You probably have to stop presenting.
So what's this? Oh, I've got to say okay. Do I? Okay. Oh yes, I see the chats now. I see the chats.
So yep. Scroll down. You can see this message is coming up now. I asked them to.
Okay. Two questions. First, do you need 4 of these modules to give 3D orientation capability? Yes. So you're right. If you're using the thruster, then to orient it, sure, but you can orient it with the magnetorquers and the reaction wheels. This is really made to translate the thruster, and then you can use the attitude control system to orient it away. So you can turn the satellite around and still use one thruster in order to change orbit. So you don't really need more than one. But if you weren't in the Earth's magnetic field, then yes, you will either have to have some kind of vector control, being able to move it around, or have multiples of them. Yes. The other question is, while you have the required exhaust velocity, 50 to 300 kilometers per second, do you have enough momentum, and how long does the fuel mass last? So the question is, yes, you're right. The momentum not only depends on the speed, but on the mass. So we would write this thruster, believe it or not, is you can try other gases and it doesn't work as well. Charge exchange works best for hydrogen. So we're limited by the mass, obviously not by the speed, because we can dial that up. How long does the fuel last? We never got to use it. We had 10 milliliters on there. We get the hydrogen from alcohol, so it's readily available fuel when you're not drinking it. So we had 10 milliliters. That was an overkill. That was going to last something like 100 hours or something like that. And we only needed it for 5 minutes. If you want to burn fuel for 1,000 hours or 3,000 hours, it's no problem. It's just a matter of having it on board. So, and it can fit thousands of hours can easily fit in a cube. If you want the spacecraft to go to be interplanetary, then yes, you'll need more fuel, more power, but that's all. Yes, that's all. That's all achievable. Yeah, Tony.
Very quick question: is the charge exchange process quantum mechanical tunneling?
The question is the charge exchange process quantum mechanical tunneling? It's not quantum mechanical tunneling. It's the electron all of a sudden finding its orbit around an atom. Quantum mechanically is more probable by the passing particle.
Yes. Okay.
But you work it out from quantum mechanics probability that it will happen. Yeah. There's another one is oops.
No, that's from Gavin on this.
Oh, oops! I seem to. Okay, so outflow. The comment of 6 thrusters is based on the several external thrusters that are needed on satellites, besides simple 3. Yeah, indeed. Look, if the thing about thrusters is they have a lot of thrust and you can do things quickly. The magnetorquers and the flywheels take a long time to orient the satellite. So if you want to do things quickly, yes, by all means, you need something like 6. Yes, and you can do this. I mean, you can make 6 of these and orient. You can have them. We have 1 thruster in 1 module. There's nothing to stop you from having 3 thrusters in that module. So it's not an issue about the actual geometry of it.
It's a payload issue, really.
It's a payload issue.
You have to sacrifice something else that's in the same volume.
Indeed.
That's basically it.
Has Joe and the team reached out to the heavy ion accelerator facility at the ANU? Apparently, space-related projects have approached them with respect to shielding of electronics. Ah, okay. Actually, I don't. Oh, no, we haven't done that. But my understanding is you can buy space-hardened electronics, but I think we generally don't do that because the budget doesn't support that. So I guess the reason you'd approach people at the ANU is to test your space-hardened electronics, because if you have your ordinary electronics, you could say, all right, well, it passed the grounded radiation test, but it doesn't, radiation accumulates, radiation damage accumulates on semiconductors. They don't heal themselves generally. So yes, it could pass on Earth, but you can imagine it failing in space as well. So, but I'm not an expert, so please don't take my word for it. What is the next phase for the development and deployment headed up on the Quava 3?
Next CubeSat.
Next CubeSat. Quava 3. Will there be a Quava 3? I think maybe not, because Quava, the actual center itself, is coming to an end. And there may be another center. It may or may not have thrusters as part of its scope. So the truthful answer to that is we don't know where this, we know it works, at least in a lab environment. We think it'll work in space, but you obviously have to show people it has. So at the moment, it's just in stasis. It's a great idea. It works. Let's put it on hold for the moment and see where we go in future. Yes, there's competition, and in the end, we may not win because there's other things. I showed you one that's on the market, the field effect propulsion system, but there's a field emission propulsion system. There are other ones coming on the market. One out of MIT has come out, and that's quite successful. They use a different effect altogether. So they're coming out, and it's competitive. And so I can't answer that question with great optimism and confidence. All I can say, it's sitting there waiting for its opportunity to maybe for the next funding or for an opportunity to make it commercial.
You want me to say a bit more about
yes,
that?
please do.
Joe
Please
is
do.
Director of
Yes.
Quava.
Yes.
So yes, we do have various other possibilities that we're talking to people about, where we would fly another one of the CXTs, or 2 or 3 of them, but they're not yet funded. So there's one potentially with Melbourne Space Program. There's one potentially with a Japanese company. There's one with a project which meant to be writing a proposal for at the moment. So a number of possibilities, but nothing definite.
Right.
But the real point really is that with Joe and Richard, and I guess I have developing this version, well, we've got designs for it. We know how to build it. Richard can knock up another couple, fairly quickly, as in another month. And they're the sort of thing that we could sell quite easily. We do now have some space heritage, as in it's been to space, it turned on in space, didn't get the opportunity to do more than that, unfortunately. But it's ready to go. So we brought the TRL up to, I think it's 7 or 8, one or the other.
Right. So it's great. There are opportunities. I should have mentioned, I've made this sort of talk more in the passive voice. I didn't attribute. 3 people essentially worked on this. The person that was funded by Quava was Richard Bowden-Reed, who did the lion's share of development and manufacturing of all this, as well as Eva and myself being involved as well. So it's a team of 3 people that developed this thing. What is okay? I think that's the questions. I think I've covered all the questions.
Well, probably about showing the sampling, and I'm trying to work out how you can hold.
Well, online, I mean, I'm not sure. They won't see any more. They had better images.
Just show it.
So I can turn. Let me turn it in front of the camera in case there wasn't an. I thought I showed most angles. Most of it's sort of. I can.
Probably just pause it a bit more.
Oopsie. So there's the electronics that you see. These are valves that control the gas. a lot of communication. The power supplies are inside. The fuel storage is inside, as well as the thruster, of course. And here's the front nozzle, and there's nothing in the back. It's just a plate that's closed off, just for access. And that's just, what does that say? That says prototype. Well, it's actually the final model rather than prototype. But and it has Quava on there, but and that's it. There's not much to this thing. It weighs, I wish I could tell you what, less than half. It weighs what, 300 grams or so. So it's not very heavy at all. Yeah, so that's basically it.
It's very compact, that's the main thing.
Yes.
And it's also got the fuel supply contained in the same container, so it's pretty much self-contained.
Indeed.
After you get the hydrogen, obviously.
Yeah. Sorry, there was a question.
Got two questions. One is the fuel, being able to generate the fuel on board with using ozone. Is it being able to generate ozone on board ozone to use as a fuel?
Oh, we haven't thought of that. We wanted the hydrogen as the fuel because
it's generated by electricity alone.
you can take oxygen and form what's called a corona discharge, basically a plasma, and it will produce ozone, as many of us have smelled next to photocopiers. We can certainly do that. We can certainly ionize. You're right. The oxygen in fact, that is occurring. The oxygen in the alcohol is being ionized. The trouble with oxygen, it has a really bad charge exchange probability. It doesn't exchange very well. Hydrogen is the best. So we'd love to use a heavy atom like our oxygen, but unfortunately, we used argon and that didn't work too well either. Yeah.
And we did use iodine too.
We used iodine, terrible stuff. It'll corrode everything. In fact, there are thrusters that are using iodine now in space. If they land on the spacecraft, I don't know what will happen. I'm surprised. Yeah, they'll corrode. In fact, I talked to a professor from the ANU who wants to do interferometry using, I think, microsatellites. But for that, he needs thrusters. He looked at iodine, of course, doesn't want them because of the corrosion. He looked at that field electric emission thruster, which uses liquid metal. He doesn't want that either because liquid metal will condense on his mirrors. Doesn't want that at all. A gas thruster like this is ideal. So you had a question.
Joe, with thrust of the order of, what did you say, nanometers?
Micronewtons. We have 5 micronewtons.
What sort of orbital control? Give me some sense of
Okay, so you can say you had 2 satellites, you need to move them within, I mean, say they were 100 meters apart, and you needed to get them closer to say 5 meters. Well, that'll let you do it within a something like half an hour or something like that. It'll let you do it. And then you need to say, if you're doing, say, I refer to astronomy because that's the most taxing one. Say you need to do interferometry, where you need to like fractions of a millimeter control. That'll let you do it because then you can control the velocity of the hydrogen, and therefore you can control the thrust to really fine degrees. So allow you to do both. Allow you to change orbit with this particular one, the 5 micronewton one, can do hundreds of meters of motion. If you wanted to really change orbit, like go from 500 kilometers to say 1,000 kilometers, all right. If you had power, if you give us the power, we'll change the orbit, and not to watts. You need to give us 50 watts, 100 watts, something like that. We'll change the orbit.
Wouldn't it be a matter of time? How much time you will spend?
And then yes, indeed, it could be lower power, but the amount of time. So we can do it. The only limiting factor is ionospheric drag. So you need to at least overcome that. But the higher you are, the less the drag there is. But yes, no, you can do it. But if that's your main thing, you say, yeah, that's my most important thing. I want to go from this orbit to that orbit. That is my major thing. Good. Give us the power, and that can be done. So it can do very fine control as a field that liquid metal thruster can. or it can do high thrust if you want it to.
The other thing that maybe is worth mentioning is that it's continuous, it's not pulse.
Yeah,
Whereas,
so
for instance, Paddy Neumann's one, pulses at, I don't remember the number, let's say 10 times a second, 1,000 volts. Bang, bang. The electronics are stuffed.
I'll just repeat what Eva, for the online people, in case Eva hasn't. There are things called pulse thrusters, pulse plasma thrusters. They are, if you look in electric propulsion books, they are there. Sometimes they're called arc thrusters. The reason people went off them is they're fine thrusters, but the first thing satellite people ask you, because they got really expensive and sensitive electronics, will they interfere with my electronics? And pulse thrusters people shied away from them because if they were high current pulsing arcs, then people had issues with them about interference with their electronics. It doesn't necessarily mean, depends on the design, you could overcome that, but that's one of the issues that they faced. So this thruster is low power, low current, continuously smoothly operating. We had sensitive electronics running the thing, and there was no interference whatsoever. So we're quite confident it'll fit snugly and happily in any satellite.
Joe, would it be fair to say that what you call the fuel is really the working fluid? Fuel is actually sunlight.
Oh, very good point. So Tony made the comment, what I'm calling the fuel is really the working fluid, and the fuel is actually sunlight. Indeed. Well, we're getting our power from the sun. Yeah. So the sun is providing, in the end, the velocity to the particle. So is the sun the fuel? I guess it is. The sun is providing the energy.
And the energy transfer is the working.
Yes. Yes, indeed. So in the end, you're not short of electrical power. It's coming from the sun. Yeah. Yeah. Okay. One more question. Sorry. Oh,
So the mass flow of the hydrogen is constant, and you just vary the velocity with it.
Yes. It's an absolute trickle. If 100 milliliters can last you over 100 hours. Right. Yeah. And by the way, we can make it last longer. It's just this is the first version, which we didn't care about. So the Hall effect thrusters have a much higher flow rate. They have 80 kilograms on major satellite of xenon. Very expensive. Xenon's a very expensive gas. Whereas with this, you don't need it. So yes, the flow rate is absolutely tiny, but you can make it even tinier. So yeah, the amount of fuel is that you can have on board is you're not limited by the amount of fuel you can have on board. Yeah.
I think, Joe, you might remember that a long time ago, Giro went and calculated that with 5 micronewtons of thrust and 100 hours, we could go from 300 kilometers altitude to 400, or from 400 to 600 kilometers altitude in 1 month, and use less than or equal to 10 grams of fuel.
Indeed. So Eva was saying that a former student of ours with this amount of 5 micronewtons thrust, we can change orbits of the order of 100 kilometers with less than 10 grams of fuel, something like that.
In roughly a month.
In a month.
So the fuel is sunlight.
The fuel is indeed sunlight. Yeah.
No,
well, there's a working fluid.
Your energy source is sunlight.
You need to define your
fuel is our alcohol in this case.
Yes.
And the part we really care about moving is the hydrogen.
Yes.
You have to ionize it, split the hydrogen off.
Yeah. I've got to say, other people looked out at our initial paper, which said hydrogen around the world. One in Germany, a propulsion team, and one in Brussels. And both emailed me saying, "Oh, it doesn't work for us." I said, "What gas are you using?" "Oh, we use argon." Well, no, it doesn't work for argon. Look at my paper. I said hydrogen. But they're old style thruster people. They say, well, you know, I've got a gas, I ionize it, I accelerate it. What's the problem? The problem is there's a subtlety called charge exchange. It's specific to the quantum mechanics of the charge exchange of that gas.
Yeah. So hydrogen's got certain characteristics which allows you to use that process, whereas the other ones are different molecules completely, and that's why they won't work.
Yes, and people are afraid of hydrogen. I told the group in Germany, switch over to hydrogen. They said they won't do that because on their system they have a thing called a cryo pump. It's a pump, basically solidifies gases. When you solidify gas and then you have to let it into the atmosphere, there'll be a lot of hydrogen, flammable hydrogen into the atmosphere. So they're not allowed to do that. Well, you need hydrogen. So the way we get around it is our system there just extracts it from the alcohol.
Well, there are two more questions on the chat.
Oh, there are two more questions.
Jeremy's put one in, so it's Julian's.
There's one about cold gas ion. Could gaseous ions at orbital altitude be utilized to augment the plasma feed, or would this be not economical?
Joe knows what he thinks.
Oh, well, I mean,
Interesting.
so indeed, the ideal thing, of course, is not to have any onboard fuel and only use the ions in low Earth orbit. We're talking about the oxygen and nitrogen, I think. So, look, this has crossed our mind. We hope to do something about it. It would certainly augment, absolutely. In fact, you'd like, at least in low Earth orbit, you'd like to replace the thruster with the orbital ions. That would be ideal. So then you don't have a working fluid. You just have electrical power from the solar panels, and that's it. So yes, the comment is absolutely relevant, and the answer is yes, it would augment, in fact, even replace. But not obviously not for interstellar, for interplanetary travel, because there's not much gas there. So the other one is, you said the fuel could last 100 hours. Yeah, that 10 milliliters could. In the prototype, how much fuel did you say you had? 10 milliliters. Sorry, no, it was not 100 milliliters, it was 10 milliliters. How long do you think you could make it last if given more time to development? Oh, no. So the trickle, we do nothing to throttle the flow of gas in there. It just goes out of that aperture that you saw. You could play games with the size of that aperture and so throttle a bit more gas. But say we left it as it is, that 10 milliliters, worst case scenario, 100 hours. It's not a stretch to have a liter on board. Now, you do the mathematics. You've got 10 milliliters, 100 hours. You've got 100 times more that for a liter. So that's 10,000 hours. You can do a great deal with 10,000 hours of burn time. And not a lot of thrusters, I think the very best Hall effect thrusters can last 10,000 hours. Maybe not that much, I'll have to check. But certainly that's pushing the limit of what has been done so far. But you can see it's possible with just a liter under the current invention. Okay, that's the remaining two questions.